All right, we're going to take a look at half-life. This is page 7 of the packet. We talked about radioactive decay and how substances break off chunks of themselves and spit that out, alpha, beta, and gamma. And half-life tells us about how long it takes for that to happen. So when we look at the periodic table, we know that different elements have different average atomic masses. So something like carbon, for example, has a mass of 12.01. That means that most carbon has a mass of 12, because that's closest to 12.01. But there is some carbon in the world that has a mass of 13 or 14. And we know 13 and 14 are less common than 12 because of the average atomic mass. And so the question is, why? Right? Why are some isotopes more common than others? So some isotopes are unstable. Again, this goes back to the idea that the nucleus has a different number of protons to neutrons, and that might not be a stable ratio. If something is unstable, it's more likely to break down into other atoms. That means it's essentially destroying itself and it's going away. This process is called radioactive decay or nuclear decay. So nuclear decay because the nucleus changes, or radioactive decay. We use those two terms interchangeably. And we can use the half-life of an isotope to figure out how much of the sample has decayed or how long it has been decaying. And this is how they do radioactive dating to figure out how old fossils are, for example. So half-life is actually a time. It is the time required for half, that's why it's called half-life, half of the atoms of a radioactive isotope to decay, to go away, essentially. Okay. And just a note here, if something has a long half-life, let's say that we're talking about one substance that has a half-life of 1,000,000 years, that means over the course of 1,000,000 years, half of the sample decays. If something else has a half-life of 1 second, that means every second it decays. If we think about which one of those two elements was more stable, the one that's more stable is the one that could last 1,000,000 years before half of it decays. The one that half of it decays every second is constantly breaking down, it's turning into something different, and it's self-destructing, essentially. So a long half-life means that our substance is more stable. And that tells us nothing about if it's alpha, beta, or gamma decay. So something that has alpha decay could have a short or a long half-life. Same thing with beta and gamma. All it does is just tell us, like, oh, if two substances, have different half-lives, which one is more able to stay that substance for a longer period of time. Okay. All right. For this, we're just going to fill in this little chart. So looking at, as time passes, as half-lives go by, how much is left over. And I'm going to break this down into two things here. I'm going to do percentage, so how much of the original sample is left as a percent, versus fraction. So it's just two ways of writing the same thing. At the beginning, when no time has passed, I have 100% of my sample. Right? So 100% of my sample is radioactive. And in terms of that being a fraction, the entire sample, we would say that's 1, right? 1 whole pie or whatever. If we wait 1 half-life, so after 1 half-life, instead of having 100 radioactive atoms, we would now have half of that, which is 50. And so that's 50%, or half of the sample. If we wait another half-life, half of this is what's left. So half of 50 is 25%, which is 1/4 of our sample is still radioactive. If we wait another half-life, half of 25 is 12.5. And 1/4, half of 1/4 is 1/8. And we could keep going, right? So if we wait another half-life, half of 12 is 6, and half of 0.5 is 0.25, which would be 1/16 of our sample is still radioactive. If I wait another half-life, that would be 3.125%, which would be 1/32. So this is kind of just looking at, if I have a sample and I wait 5 half-lives, only 3% of it is radioactive. If 100% was radioactive at the beginning, 5 half-lives knocks that down pretty substantially. We can use this idea to help us figure out how much of a radioactive sample is left over time. So for our first part on here, how many milligrams of a 10 milligram radioactive sample are left after 3 half-lives? There's a couple of ways to solve this. The first would be to look in our chart and see after 3 half-lives, I have only 12.5% of my original sample is radioactive, which is 1/8. So I could use the idea, so here's method 1. I could use that chart to say 1/8 is radioactive from the chart above. And if 1/8 is radioactive, 1/8 of 10 is what? So 1/8 of 10 is, I could plug this in my calculator, 1.25. So 1.25, I'm just going to put the units on here, milligrams, is still radioactive. So that's method 1, is to use this little chart that we made and take that fraction and use that. Another method, and this is the method that I like in general because I think it helps you kind of understand, is to use like a timeline. So tell the story or make a little timeline. So at the start, how much did we have? We had 10 milligrams that was radioactive. And our question is, how much is left over at the end? Well, I need to know how many half-lives we went through, 3. And the definition of a half-life is how long it took for my sample to divide in 2. So I need to let this go through 3 half-lives, which means that I need this to divide by 2. That's 1 half-life, 2 half-lives, 3 half-lives would give me my ending amount. So in order to go forward in time, my sample just divides by 2, divides by 2, divides by 2. And I could type that into my calculator. 10 divided by 2, divided by 2, divided by 2. That was each half-life. And that's going to get me the exact same answer, 1.25 milligrams. Okay. I like the story or the timeline method just because it is going to help you when the problems start to look a little bit different and they're written a little bit differently, or we're solving for a different variable. If you kind of know what the story is, then you can work backwards or forwards through the problems. All right, so for our next one, a sample of a radioactive material decays for 4 half-lives. After this time has passed, there is still 15 grams of radioactive material left over. How much radioactive material was there originally? So in this case, we're actually given information about the end of the story. So if we look at our timeline method, at the start, how much radioactive material was there originally? I don't know. How much was there at the end? There was 15 grams that was still radioactive at the end. And I know that this went through 4 half-lives. So that means that to get to the start, from the start to the end, I had to go through 4 half-lives. So I'm just going to write that out. And so when I look at this, I'm trying to figure out what number, when divided by 2, divided by 2, divided by 2, divided by 2, would get me 15. Well, if I need to work through the problem this way instead, what I can really do is say, well, if I'm dividing by 2 to get to the end, what if I start at the end and I want to go back to the start? I could multiply by 2 and multiply by 2 and multiply by 2 and multiply by 2 to get back to the starting amount. Okay, so if I do 15 times 2, that's 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. I'm going to do that on my calculator. That would get us 240 grams that we had at the start. And when that divided by 2 4 different times, I ended up with 15. And the other way to do that, if you look at 4 half-lives, this ending amount is 1/16 of the starting amount. And so to go from the end to the start, I would have to multiply by 16. So 15 times 16 would get us 240. So that's kind of our other way of doing it. You just have to be careful if you're, in the first problem, we multiplied by 1/8, But if we're moving backwards in time, instead of multiplying by the fraction, we would just multiply by the bottom part. So that's where you kind of have to be careful about which method you're using. Just remember that at the beginning you had more that was radioactive, and it decays or it reduces over time. All right, I'm going to do the story method for these last two. So a 50-gram sample decays to 12.5 grams. This is the start of the story. How much did we have at the beginning? 50 grams. At the end, we had 12.5. And we want to know how many half-lives have passed. How many times did we divide by 2? So if I just say, well, what if it was 1 half-life? 50 divided by 2 is 25. That's not the end. So let's try another one. If we had 50 divided by 2 was 25, 25 divided by 2 is 12.5. So that does give me the answer. How many half-lives was this? I divided by 2 different times. Each time I divide by 2, that's 1 half-life. So here's 1 half-life, here's 2 half-lives. So 2 half-lives passed in order to get from 50 to 12.5. All right, our last one on here. There are 5 grams of iodine 131 left after 5 half-lives. Just as a note, half-life, in order to figure out how much we had at the beginning or the end, I don't even need to know what the radioactive substance is because it doesn't matter. So that's just extra information that we don't really need. So I'm just going to cross it off so that I don't get tempted to put 131 somewhere. Okay. Our question is, what is the mass of the original sample? This means that we're being asked, how much did I have at the start? Right? So how much did we have at the start is what we don't know. We know that we've waited 5 half-lives. So whatever we had at the beginning got divided by 2 5 times because it went through 5 half-lives. And that gave us the ending amount of 5 grams. Right? So in order to work through this problem backwards, I don't have this number to divide by 2 a bunch of times. I'm trying to find it. So when I'm trying to work backwards through this, I'm going to take 5 and I'm going to multiply it by 2. Multiply it by 2, multiply by 2, multiply by 2, multiply by 2 in order to get back to the start. So if I do that in my calculator, I can do that in my head too. So 1 half-life ago we had 10, then 20, 20 times 2 is 40, 40 times 2 is 80, 80 times 2 is 160. That's how many grams we had at the start of the problem. Okay. So when we're looking at these, again, that storyline method I think is really helpful. You could also use that little fraction chart if you find that more helpful.